In this hour, we're going to talk about our very first algorithm. And before that, I'm going to um, show you some important concept while you are using AI or machine learning. Okay, the first concept is model. And the first question is, what is a model? Very similar to toy model. Okay, for example, the subject is, for example, a car. Okay, a car is much bigger and it is very expensive, right? But you can buy a toy model of a car. So the car is a little bit smaller and not that accurate as a real car, right? Maybe the door cannot be opened. Maybe the wheel cannot be turned. Maybe the toy model, the car model, is made by plastic, not steel, right? So when we talk about model in machine learning or data mining, the model is some kind of thing that can describe a subject, but the model is more simplified. Okay, it is more simplified. Uh, so let's take a look at this definition. Okay, the toy model is a deliberately simplest model. Okay, so with many details removed. So because a real model, for example, a real car is too big, so you cannot take it to your room, right? So sometimes we need a more simplified model to describe the subject we would like to analyze. So there will be many details to be removed from the real subject, so we can simplify the subject we like to describe and we like to analyze. Okay, so while preserving important and necessary characteristics, again, for example, a car should for example has four doors, right? It has four wheels and some characteristics so that you can identify it is indeed a car if you have a car model, right? So that it can be used to explain something concisely. Okay, so for example, there are several different kind of subject you can describe. For example, a car, okay, airplane, and house, or even human beings. For example, a kid in the kindergarten, or malicious software, an attack, behavior. You can describe anything you like to describe as the subject you would like to model, but it depends on how detailed you can describe this model. So if you describe something very in details, right? So that would be a better model, right? If you describe a model with a very limited characteristics, or you model something with some unnecessary characteristics, then that model will not be that accurate, right? So think about toy model when we explain model we use in artificial intelligence, okay? And usually, the best model of a subject is exactly the subject itself. For example, if you want to describe a car, you want to model a car, the best model of this car is the car itself, not a smaller one or a plastic toy, right? But from the perspective of data mining or machine learning, it is very difficult, or it is a little bit hard for you to analyze such a complex subject, because a car has so many characteristics, so many parameters, so many things you need to describe to make a real car. But that is not that efficient for us to analyze a car. So we need a more simplified way to describe a car. So we need a model. Okay, we need a model. So let's take a look at the this one is the data table. So let's go to here. Okay. When you try to analyze some subject or some data, okay, I think the most trivial way to use a data table to analyze some subject. For example, there is a table, right? We have n rows, right? N rows, and you may use several different columns, or we say features, to describe something. Okay, so we have n samples. For example, each of the rows, each of the samples is a kid, is a child in the kindergarten. Okay, so we have n kids. Okay, and you can use several different features, several different columns to describe this kid, right? For example, the gender, boy or girl, how height, okay, their weight, okay, their age, where they live, okay, which neighborhood, and what she or he ate in this morning. You can describe a kid in a very, very complex, more very detailed way to describe a kid. So you can use a bunch of features to describe a kid, and for example, we have n kids in this data table. Okay, in this class, okay, we have several different data which is related to cybersecurity, and the number of samples we use in the classroom, maybe there are a few hundreds or a few thousands to demonstrate some algorithm. Okay, we use some data set, and the number of fields we use in this classroom, maybe there are tens or a few hundreds. So that is not that big, right, from the perspective of big data. Okay, but in some real-world application, the number of samples we collect, maybe there few millions, even billions. Okay, and the features we talk about in the real world, maybe there few hundreds, sometimes thousands. So as you can see that this table right here, that will be a very huge table to store all the information about those n samples with their m features. And the features can be very complex. They can be a number, for example, height, can be some categorical data, for example, the color of their hair, black color, golden color, red color, something like that. Or even, for example, address. It can be very complex. So to describe the kid in the kindergarten, okay, we can use this table, n rows times m features. But as I mentioned, this table can be very huge. So from the perspective of model, we don't want to remember all those complex, detailed information about the kids, how to describe kids. So we have a concept that can we use some mathematic tools that can help us to simplify this table. So that is the reason why we call that is a data model. We use some algorithm to create a model of a subject. The subject is quite complex. The number of samples is quite large. The number of features is quite large. And can we use some more simplified way? And most of the time, there are some mathematic tools that help us to describe this subject in a more simplified way. So that is the reason we call it model. Okay, and sometimes, I will show you right here. So the big X is the collection of all the features. Okay. So sometimes we use this big X to represent all the features in this data. Okay, and the other one is this lowercase y, that is target. Okay, sometimes when we describe some subject, okay, we have a table like this, right? And we have a target column. That means we would like to model an application. Okay, so the application is to describe how do we use those features, which is big X, right, to find the relationship between big X and another spatial column, which is Y, which is a target. So we like to find the relationship between the big X and the small y. Let's take a very strange example. For example, the left-hand side of the big X is the information about the kids in the kindergarten. Okay, we have several different kids right here. And at the right-hand side, we have a very strange application, which is the salary, for example. Salary. That means if I can collect the information about kids right here, right, and maybe 20 years later, I can collect the salary of his or her first job, and we can put this number right here in the Y column, and we can use mathematic tools to help us to find the relationship between the big X and big Y. I know that is a very strange application because it really makes no sense. Okay, right here, for example, the x1 is the height of this kid, and that is the weight. Okay, that is the breakfast sure he ate in this morning. Basically, you can collect a lot of different features. Even the features is quite strange, like the breakfast sure he ate in this morning. And the target can be any arbitrary things you like to figure out what is the relationship between this target and the features. But from the perspective of mathematics, if you given this big X table and its corresponding Y, the mathematic tools can help you to find the relationship between X and Y, and in a more simplified way. So that is what we call it as a model. Even if the application is very strange, make nonsense. Okay, we will talk about some other concept in the later class. Okay, but that is the things you would like to know. So it would be better that the algorithm we use okay, to create something like that is the model 1. Okay, it can help us to find the relationship between big X and Y. So the simplest I think the simplest way is to make a mathematic function. So we can use a mathematic function which is G. Okay, it is an M1 model. We input the features as the parameter of this function, and it will output a value. Okay, but we put a hat right here because it depends on how good your G function is. The output is y hat. Y hat is not necessary to be exactly the same as y, but it should be close to y. And the G function right here is what we call a more simplified way to model the relationship between X and Y, because you're given an example, you're given a sample, and there are some very complex mathematic things in G function, but it outputs y hat, which should be close to y. Okay, that is what this is the way we express, okay, the data model. Okay, and but that is the model we made, right? But you have to think of one thing. If there is a oracle or God, okay, there indeed has a function which exactly can output the exact y, which is the target. Okay, maybe there is a magic function f which can output y if you given x, but sometimes it is very difficult for us to find such kind of f function because the f function could be very complex, even too complex for mathematics to model such kind of f, such kind of relationship between big X and y. So instead, we use a simplified way to find a g function and make sure it can output y hat, which is close to y. And think of something. We can also use another mathematic tool to find another g function which is M2. It also can output such things, right? So of course there are several different mathematicians or statistics experts. They design several different algorithms to generate different models, like here G model 2 or G model 1. So it really depends on what kind of algorithm you want to use to analyze this n data with n features and the corresponding y. There are several different algorithms we will teach you in the later class. Okay, maybe we have not 10 different algorithms. Okay, but after we learn several different algorithms, the next question is, which model is much better than the other one? Okay, so that the first question is, after you have such kind of data table, and what kind of model, what kind of algorithm you can use to model such kind of data. And the second question is, there are several different models, right? There are several different algorithms. So which one is much better than the other one? Okay, from the perspective of application, we usually, okay, we choose the best one. But what is the definition of best? So that is the second question we'd like to talk about. Okay, so after you have for example, after you have a model, and then we can collect the second data set, which is called data set. Okay, the first data set is called training data set. The training data set is used to help us to find the different models. We apply different algorithms on the training data. So we have n data points, we have n features, like y. So those data, okay, is called training data. We use this training data to help us to find appropriate model. And after that, we can collect the second data set, which is called testing data. And we can input the data we collect in the data set to the model we generated from the training data set. And also we can, and then we can output its y hat, right? So right here we have y and we have y hat. Again, we can check against it with the y and y hat to see if the model is appropriately created or generated. If y is still in the testing data, if y is still close to y hat, and we say, okay, that model is good enough. And if the y hat generated by the model is not even close to the y, and we say, okay, that model is not good enough to predict the y value in the testing data set. Okay, so that is, I think that is the basic concept of model, and we will go over some definition right here. Okay, so follow me. Okay, So table is a very straightforward way to present data. Okay, it has n data points. Okay, each data point is represented by m features from xe to xm, and we use a big X to represent the collection of XO features. Okay, and there should be a specific column which is y. So with this specific column y, we can generate an application to use big X to predict y. In order to do such kind of prediction, and we need a model to find the relationship between big X and y. So we have a big model right here. Okay, so as we mentioned, the best way to model a subject is to use the original. As I mentioned, if you want to model an aircraft, the base model of the aircraft is the aircraft itself. It's not a toy model. But as I mentioned, the best way to represent the data is to keep the entire data table, but from different perspective. From the memory perspective, we don't have such a big memory to store all the information of n and m, right? From the computation perspective, the table is too big for us to analyze, to do some computation. So it is not a feasible way to preserve all the data in the data table. So we need to find a more conscious way to represent the data and to find the relationship between x and y. Okay, so small y is target, the big X is the O features, and we like to find some model, which is a mathematic model, okay, to help us to compute or predict the y hat by using y. Okay. So to find such kind of model, we have existing n data point, which is what we call n training data. Okay. And for to find such kind of model, okay, we need to apply different algorithms. But those algorithms, there's several different algorithms, but not all of the algorithms can find the relationship between different types of data. Okay, so basically, the algorithm is divided into two different categories. It depends on the target y is a numeric field, or target y is categorical. For example, yes or no, class A, class B, class C, black, green, red. That is categorical data. Okay, so if the y is numeric, and the model is called regression model, and we need to use some regression algorithms. And the other one is if y is categorical, and the model is called classification model, and the algorithm we use is called classification algorithm. Okay, so we have two different types of algorithms. It really depends on the target y you use. Okay. Okay. So right here. Okay. So the G is approximation of f. F is the real relationship between that big X and Y, or you can say that is the oracle. The oracle knows the relationship between X and Y. Okay, but we cannot model such kind of we cannot describe such kind of function, so we use G to model F. So G is an approximation of F. Okay, so the y hat is the prediction value of model GX while observing big X. Okay. So so right here we would like to introduce our very first algorithm, which can help us to find the model of big X and Y, which is called linear regression. Okay, And before that, I would like to talk about this one. Sometimes, okay, sometimes the table we obtain is like this. It's very classical, right? Several features and it has a white color. So for such kind of table, okay, if we use a model to find the relationship between x and y, okay, such kind of algorithm is what we call supervised learning. That means we have a y. That means we have y. So we have a target. So while we trying to model the data, we're trying to learn the relationship between x and y using these n data points. And the algorithm is called supervised learning. Okay, so the first few of the first 3 or 4 class, we will teach you a lot of supervised learning algorithm. Okay, to find the relationship between x and y. Okay, but sometimes, okay, the data we obtain has no y. Okay, that means the data has no specific target to learn. So we have another approach, another set of algorithms, which is called unsupervised learning algorithm. So in that kind of algorithm, okay, we are trying to figure out the relationship within the x, within the n data points. But we'll talk about how to do the things in the future. Okay, so we just keep it in mind. Okay. So let's take a look at the first one. Is called linear regression. Okay, so we have 20 data points right here. So it is just an example. Okay, it is very simple that we have only 20 data points. So n is 20, right? And right here we have y column, right? So that is supervised learning because we have a specific target, right? And we can see that is only one x, so the big X has only one component, which is x1. So we'd like to find a model that can describe how to do such kind of things. Okay, the reason why we call this the algorithm is called linear regression is that if we plot the x and y, okay, x1 and y in the surface, and we can, human beings is very smart, so we can see that, okay, that it looks like x1 and y, their relationship is a line, right? So that they are linear. So they are linear, and we can draw such kind of things. Okay, so if we want to represent all those 20 data points in a more simplified way, we can use a line to describe this n data point. And as we know, a line in the surface, okay, the equation is y equals ax1 plus b, and a and b right here is the parameter of this line, right? A is the slope and b is the intersection, right? So although we don't know how exactly the distribution or how exactly this data point is created by f function, although we don't know, but we can use some way to create a model. For example, that's the model 1, okay, and that is g of x1, okay, and we know it looks like linear, so we can use a line to describe it. So we can simply use a very simple mathematical way to describe a line, and this line describe these 20 data points. Okay, and we wish G will be very, very similar to the oracle function, which is f function. Okay, so we use these 20 points to figure out what is the slope and what is the intercept. That is slope, that is the intercept. Right. And as I mentioned before, there should be some other model, for example, M2. Okay, it is GM2 x1, and it is AX1 plus B, and that's M2. Okay, AM2, BM2. Okay, that is AM1, AM1, BM1. So the green line in model 1, it could be this line, M1. And the purple one, it could be another line generated by another machine learning algorithm. It can be this line, M2. Right? But as I mentioned, human beings is very smart. So basically, if we take a look at these two lines, I think the M1 is a better model to model these 20 lines, because those dots, those 20 data point is much it's aligned with the blue line, right? Better than the purple line. That is a different model, and of course, you can use any other mathematical tools to help you to find another model, which is GM3. And it is not necessary to be linear. This line can be very strange like this one. But as we mentioned before, if you want to describe a line like M3, you need a lot of parameters. For example, it could be 5x 15 . You know, you can use any polynomial weight function to describe a line. It can very, very fit those 20 data points, but that is not what we want, because that model would be too complex. So sometimes we would choose a more simplified model like M1 or M2 to describe the data. And as I mentioned before, that is our very first algorithm. So we only use a very simplified line to describe the data we collect right here. So the next question is, if we have two lines, for example, the red one is called M1, the blue one is called M2, right? So that is, right? M1 has another, that is M1. And how do we compare these two different models? Although they are both linear, but they have different slope, they have different interception. But how do we compare this model? Which one is better? Okay, so we introduce important concept is called error. Okay, so take a look at this data point. Okay, that is P0. Okay, so P0, you can find the X and Y in the data table, right? For example, that's X0, Y0. Okay, you can find this value in the data table, right? Okay, let's first look at this model 1. If you use P0, X0, okay, the y hat of M1 is that is GM1, right? That is GM2. Okay. The red one. So the y value is GM1 x0, and it's right here. That is x0, y0. So we can remove this one. Okay. For the p0, its x value is x0, its y value is y0. But if you use x0 and put it into the gm1 function, the result is gm1, right? G hat m1. And for the blue one, okay, it's right here. Y hat m1 gm2, okay, gm2 x0, okay, it's right here. And as we can see, if you put the same x0 into the gm1 function and gm2 function, and you compare it with the original y0, okay, and you can see that the arrow which is the distance between this, sorry, blue one, okay, the arrow between actual y0 and the ym2 hat is that, right? And the arrow between the actual y0 and ym1 is that the height is that. And we can see that that is a little bit, that is the height is different, right? So for all of the 20 data points, we can calculate the arrow of all data points. The blue one I draw here is the arrow of the real y, and for all the y hat in M2, right? You can see that the arrow is right here. And for the model one, okay, we can see that all the arrows between the actual y and the prediction value of gm1 is here, is the red lines. And we can see that apparently the sum, okay, the sum of all datas, their arrows between the actual value and the prediction value is right here, and we can divide it by n, so that is the average arrow of these 20 data points. Okay, we can use this value to evaluate the different models, and this value is called MAE, which means mean. That it means we divide it by n, right? And we summation all the errors. So A is absolute. That means the absolute distance between the actual value and the predict value. E means error. That means we find the difference between the actual value and the prediction value. So that is called MAE. If MAE is large, that means the line is a little bit far away from the data point. If MAE is small, that means the line is quite fit to the 20 data point. Okay, so that is one of the way to help us to compare different models. The smaller MAE, the better the model. Okay. And there's another concept is that, okay, some mathematics believe that, okay, we don't simply use distance to do such kind of comparison. Okay, we made all those distance with square them. Square. So we have another evaluation, which is square, and that is called mean square error. So we have a square right here. So basically, we have a lot of different red squares, right? And we have a lot of blue squares, and we compare what is the average square error of the blue model and the red model. And the concept is the same. Okay, if your model is not that good, it's not that good, the square, the sum of the square right here will be bigger if your square, which is the blue one. Okay, there's some little square right here. If your model is better, and your MSE value will be smaller because you have smaller sum of the square, the area of the square. So basically, that is the way we evaluate different models. Okay. There are two important things we have to mention right here is that, okay, after you obtain the data points, okay, the first thing you need to know is what kind of model you would like to adopt. Linear model, or even for example, linear model is like this, right? The form of linear model is like this, but you can use another form to describe a line, to describe the data points, right? And it can be very, very complex. But in machine learning or in data mining, there is no good way to help you to identify which model can describe your data better. You have to decide which model you want to use by yourself. There's no some magic way to help you to find the perfect form of the model. So you have to decide by yourself. And the second thing is that in the later class, we will teach you some other different ways to evaluate or to compare different models. So MAE and MSE are two of the popular ones. But the second thing is you as an analyzer, you have to decide which function, which comparison function, MAE or MSE or some other function, you would like to use. You, as a data analyzer, you have to decide which model you want to use and which function you would like to use to evaluate different models. Okay, there's no magic way to do so. You have to do it by yourself. So that is the the definition of MSE, right? So it's right here. Okay, the next thing I would like to talk about is the linear model. Okay, if you have only one parameter, or say one feature, right? If you have only one feature, okay, the model you create between the x1 and y could be this one, right? But if you have a lot of features, the model you create might be looks like this one. Because for example, if we have n features, right? So to create a linear model, we need to have some parameters right here to until theta m to times xm, right? If you have m features and your linear model should look like this. Okay, so theta right here, okay, is a collection of all the parameters we use in the big theta. Okay, the big theta is the collection of all the factors of the linear model. So that is a general form. Okay, it is not necessary to be one feature and a line. Okay, for such kind of general form, it can be m features with m factors and plus 1, theta 0 is the interception value. Okay, so that is sometimes we write a linear model in this way. Okay, and there's still some other way to represent a linear model. So for example, sometimes we can present your model by this way. For example, there's x, okay, x1, x2, x3, xm, right? That is how we use a vector to represent m features. Okay, so if we have a weight, okay, the weight is exactly the same as the theta. Okay, so that's weight 1, weight 2, weight m. So in order to create this form, right, so we simply just transpose the weight. Okay, so it becomes a vector like this. It's a row, right? So weight transpose, okay, times, okay, we say product, okay, product x. Okay, so this one would be w1x1 plus w2x2 plus wmxm. That is just another way to represent a linear line. Okay, and you can see that there should be a intercept value right here, right? So sometimes, okay, we write it in this way. Sorry, weight 0, sorry, time product x plus theta 0. Sometimes we write it in this way, or sometimes we write it in a strange way. Is that we put a 1 right here and put w0 right here. So in this case, okay, there's a w0 in this vector. That is just another way to represent a line in a space. Okay, a linear way to a linear line to. It's just several different representation. Okay, you can write it in this way, you can write it in this way, you can write it in this way, which is fine. Okay, because they all represent the same thing. Okay, the next thing is right here. Okay, because the MSE is a little bit big because it has a square, right? So sometimes we have RMSE, which means root square of the MSE. Okay, it's just a definition. Okay, so after we introduce all the concept, okay, you have to try it by yourself. Okay, there are several very useful package in Python. Okay, you simply just import those libraries, and you can see that for those packages, you simply just give them the big X and the small y, and they can tell you the interception and the coefficients of the features. So in this way, okay, the y hat, this model, okay, the model linear regression model, okay, its y hat equals 1.x1 minus, that is the model we find out, represent the relationship between x1 and y. Okay. For such kind of because we have several different models, right? So there should be one model. Okay, we have a star. Star means optimize. There should be a optimized model. Okay, it's y hat. Okay, as a star x1 plus b star. Okay, it's theta star. That's all its c parameters include a star and b star. No matter how many models you have, but there should be one model which has optimized a star and b star. So its corresponding MSE value is MS star because it is the minimized. It has a minimum value of MSE. As you can see that M1 and M2 has a MSE value, right? But if you have if you change the slope, which is A, you change the interception, which is B, you can tweak the line to have the minimum MSE, and no other line has smaller MSE. So if we can find such kind of model, and we call it as the optimized model of this linear regression, it has a perfect slope A star and a perfect intercept B star, and it has the minimal MSE value. So that is called M star. So by using those packages in Python, we can easily find the M star. So basically, you don't have to write all those mathematics things to find the smallest MSE value of a model, but you simply just use the package, which is okay for me. It's okay for me. Okay, there's some definition of MSE right here. Okay, we can skip them. But before we introduce next algorithm or some other things, I would like to show you how to find such kind of optimized model, okay, by using the linear regression as an example. Okay, so we stop right here. Okay, we continue next hour.